Warning: the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, Professor of Mathematics at Cosumnes River College in Sacramento, California. And if you are watching this video series, you now know we're stepping into exponential and logarithmic functions. Now, this should be a massive review for you if you are in pre-calculus. You should have encountered this stuff in college algebra in your trig course and in your algebra 2 course. So the way I'm going to treat it is as if you have seen it before. And I will only take high level examples here. So this should be a high level review for you. So let's get started. All right, graph the function, state the domain, the range, and the asymptote. So notice that I immediately just start into the fact that you should already know this is an exponential function because it has an unknown in its exponent. That's what makes it an exponential function. Notice I'm not even writing the definition here. Another thing you should note before we even begin or go any further is that the base of that exponent is not allowed to be a negative number. So if we call that the base, it has to be greater than 0, and it cannot equal 1, actually, because if it equaled 1, well, then you have 1 to a power. Well, that's just 1. So it doesn't make sense to call that an exponential function. So that's just a heads up. You should know that. You should also know, for example, that if the base, in this case it's 1/3, but let's just write it off to the side. If the base were greater than 1, then we have exponential growth. And so the exponential function itself is increasing over time. Now, something that you should possibly recall from your Algebra 2 course is that exponential functions have what is called the base multiplier property. And the base multiplier property essentially says the following. Given some function that's exponential, so we have an exponential function a times the base b raised to the x power, well, the value of y, the output, gets multiplied by the base b for each increase of 1 in x. Now that's probably not how you've heard that in the past, but that is very true for exponential functions. So I'm going to scroll down a little bit, and you have to forgive my screen. My Wi-Fi is just terrible right now, but at least we can kind of get this done. So let's take a look at a table really quickly. So we'll create a function, f of x equals 3 times 2 raised to the x. If you let x equal, for example, let's start with actually something not so traditional. Let's start with x equals -2. If x is -2, you get 3 times 2 to the -2, or 3 over 4. And then if you just bump up by 1 in the x value, the output is 3 times 2 to the -1st, or in other words, 3 over 2. Notice that that is actually twice 3/4. So we multiply 3/4 by 2 to get to 3/2. And let's go ahead and move forward a little bit. Let's go to x equals 0. Again, we took a step by 1. That's 3 times 2 to the 0th. Well, any non-zero number raised to the 0th power is 1. So that's 3 times 1, or 3. And again, notice that that step size of 1 in x led to a product of 2 in the y value. So we multiplied the y value by 2. And now that you can kind of see that pattern, there's no real need for me to plug into my function. I could just write 1, 6 and 2, 12 and so on and so forth down the line, because each step is just multiplying the y value of the previous step by 2. And that's what I mean by the base multiplier property. Every step of the way, you're just multiplying the y values by the base. Let me zoom out a little bit. Now, I said all that in the middle of actually talking about graphing this function. Let me finish my green ink over here. So if we had an exponential function with a base greater than 1, then it should make sense by the base multiplier property that the function is increasing, because every step of the way you're just multiplying by a number larger than 1. Likewise, if that base is less than 1, but remember it has to be greater than 0, then every step of the way we're multiplying by a number between 0 and 1. We're shrinking our y values. And when you have an exponential function that's decreasing, we call it exponential decay, or that it has or is demonstrating exponential decay. And when you have an exponential function that's increasing, we say that you are witnessing exponential growth. Well, all of that is in preparation to talk about this function. And again, it's not your computer screen, it is my Wi-Fi. So I have to just get to a static screen so it stops breaking up. But here we go. We're going to graph this function. And the fact that this base of this exponential function is less than 1 in magnitude, or actually just less than 1, between 0 and 1, we know that this is going to be exponential decay. So I know that for a fact. Now, the main thing you want to note here as well is that you have experience with exponential functions, so you should be able to graph this exponential function using transformations. That is, you should be able to note, you'll take your base exponential function of 1/3 to the x, you'll stretch it by a factor of 2, and that's a vertical stretch by a factor of 2. You will also shift right by 1 unit, so that's shifting the base graph right by 1, and then shift up by 4 units. Now, I have to tell you that as you're going into calculus, you need to know this like really very quickly. You shouldn't even need to graph this function to know what it looks like in your head. That's how you want to be when you step into a calculus course, that you're that familiar with exponential functions and logarithmic functions, which are not part of this lecture. To be painstakingly slow with this, let's go ahead and just graph y equals 1/3 to the x power. It looks something like this, as all exponential functions, whoops, no it does not, it's decreasing. It looks something like this. I won't edit that out because it's okay for you to see that I will make a mistake every now and again. Y equals the quantity 1/3 to the x. It's a decaying exponential function. I caught it, by the way, once I was about to write 1/3. I realized, whoa, that's totally wrong. Now, if you allow x to be 0, and by the way, normally you would not graph these by plotting points, but as anybody who's watched my videos knows that I really try to showcase that you should have 2 anchor points that you keep track of through all your shifts and transformations when you're doing graphing by transformations. So in this case, when x is 0, the y value is 1, because 1/3 to the 0th power, well, that's 1. And I'm going to actually choose an x value back here of -1. And if I do that, well, if you allow x to be -1, you have 1/3 to the -1st power, or 3. And I do that very quickly in pre-calculus because you have dealt with the laws of exponents for 3 courses prior to this, so there's no need for me to explain how I did that. All right, notice the scale there is completely whacked. It's not exactly the right scale, but that's okay. I'm just chicken scratching out a graph very quickly. All I really want to know is, what are those numbers on the curve? And if there are any asymptotes, I want to note them right now. So notice there is a horizontal asymptote. All exponential functions have a horizontal asymptote. And right now it's at the x-axis. Now I'll just, as you probably know from watching my videos, I'm just going to go ahead and treat the transformations from left to right in this statement right here. So the leftmost transformation is a vertical stretch by a factor of 2. That is, we're going to multiply all the y values in this graph right here by 2. That's all. It's going to look essentially the same, but you're going to just double up the y values. So I'll just quickly sketch this out. Notice I didn't even bother changing the ink. All the y values are multiplied by 2. So I'm just going to call that -1,6. The scale, again, completely whacked here, but that's okay. Nothing wrong with that. We can fix that later on. And again, I'm going to note here that this is now y equals twice 1/3 to the x power. And now I do, if you're in an Algebra 2 class or a college algebra course, I take my time with the last 2 steps, but because you're in pre-calculus, you can do the last 2 steps as a single step, where we shift right by 1 and shift up by 4. So I'll do that right here. First, note that I made my axes somewhat larger, mainly because this will be my final graph. Also, I should probably label my axes X and Y. And I labeled the X-axis with a 1 there. Now, I do want to mention that I have to pay very close attention to the y values. If you look at the y values of our most recent graph, they're 2 and 6, and we're lifting all the y values up by 4. So that's going to be, instead of a y value of 2, it'll be a y value of 6, and instead of a y value of 6 on that second point right here, it'll be a y value of 10. So I have to choose my y scale appropriately here. So I think what I'll do is I'll go by 2s. So I'll call this 2, 4, and 6, and 8, and 10. Just makes sense. Now our horizontal asymptote was originally at y equals 0. But again, that even lifts up by 4 steps. So I'm going to have a horizontal asymptote at y equals 4 instead of 0. And I'm just going to quickly dash out some values here. It's a little lopsided, but it will do. And the point that was at 0, 2 is now at 0, 6. I'm going to use blue for that. There we go. But it's actually not at 0, 6 either, because it also shifts to the right 1 unit, right? Our entire graph shifted to the right 1 unit. So it's going to be at 1, 6. So I'm going to actually plot it at 1, 6. And our other point, which is at -1, +6, is now at 0, 10. Something like this. And really, I only need those 2 anchor points, and I can graph the rest of this curve. Now, it is going to be approaching this horizontal asymptote, and I'll go ahead and try to chicken scratch out the graph. And there we go. I think that's pretty good. This is going to be, again, I think it was f that we called that. Yeah, f of x is equal to 2 times 1/3 x minus 1 plus 4. That level of detail, you need to have at least that level of detail when you're graphing in pre-calculus. You definitely want all that stuff. And by the way, we should probably make sure we've answered the entire question, which we haven't. We've graphed the function, stating the domain. Domain of exponentials is all real numbers, so you can plug anything in you want. So I'm going to go ahead and note that down below. And the R double bar just means all real numbers. We also want to state the range. And the range is a lot easier to see once you graph. That's the one thing about domain and range. Domain is usually very easy to find. Well, I don't want to say easy, but it can be found using methods, algebraic methods, by hand without graphing. But range of a function often requires you to graph the function. It's all the possible y values. So if you take a look at all the possible outputs for that blue curve there, it's everything from 4 all the way to infinity. Those are the y values. It will never touch y equals 4. So the range goes from 4 to infinity, never touching 4. Again, very important that you can do this super quick, actually, in calculus. And finally, we were asked for the asymptote, and that's just y equals 4. That's it. That's the entire graph. And most graphs of exponential functions are that quick, if not faster than that. Notice, I think I mentioned it earlier, but this is titled Advanced Topics in Exponential Functions, mainly, again, because you have seen this stuff before. So let's try something else here. What's another advanced topic in exponential functions? Well, finding equations of exponentials is kind of critical. It's not that you're going to be doing this all the time in calculus, but you still need the skill because it's going to just happen that you need to find the equation of an exponential. And to do this, we're going to use a system of equations. Technically speaking, you can use a system of equations to find the equation of a line. You can use a system of equations to find equations of parabolas or cubics if given enough points. And likewise, you can use a system of equations to find the equation of an exponential function if you're given a couple points. It's kind of critical here that they let us know it's an unshifted exponential function. If it's a shifted exponential function, all bets are off. But luckily, you'll never be asked that. It will always be an unshifted, so don't worry about that. So how do you do this? Well, you start with the base idea of an exponential function. So what does an exponential function look like as a formula? Well, it looks like f of x equals a times b raised to the x power. We just don't know what a and b are. Notice, again, I'm going to say it out loud. We have two things we don't know, a and b. In any equation or any part of mathematics, if you don't know n things, then you need n constraints, or n points in this case. So we don't know two things, a and b. Luckily, we were given 2 points on the graph. So we should be able to identically find a and b. How do you do that? You plug in 54 for the output. So I'll do that right here. And plug in -2 for the corresponding input. Now, obviously, that does not tell you what a or b are. However, you can do the same thing again with the second point. You let the output be, I don't know why I'm writing implications because it doesn't really work like that, but you let the output be 2/9 while the input is allowed to be 3. Now, there are several different ways to solve this. You could technically, because this is now a system of equations, you could technically solve the first equation for a or b and insert it into the second equation. That would work perfectly fine. So you're more than welcome to do that. I do these slightly differently because I like to. No other reason than that. So I'm going to show you the way that I do it. You don't have to do it this way. If you're not a student of mine, or if you are a student of mine, you do not have to do it the way I'm showing you. You could just solve one of those equations for a or b and substitute it in the other equation and solve that system like that. But I'm just going to show you something here. I'm going to call the top equation equation 1 and the bottom equation equation 2. And what you can do is you could take equation 2 and divide it by equation 1, or vice versa. It doesn't actually matter. But I'm going to take equation 2 and divide it by equation 1. And what I mean by dividing equations, because technically that's not a mathematical operation, dividing equations. However, the concept works here. So we're going to take that second equation, which is 2/9, and we know that 2/9 is supposed to equal a times b to the third. And we're going to divide both sides of that by the second equation, or sorry, the first equation, which is 54 and a times b to the -2nd. So all I did was basically create a couple fractions, the numerators of which were equation 2 and the denominators of which are equation 1. What's nice about that, and by the way, you can really only truthfully do this with exponential functions, not with linear or quadratic or polynomial functions. So just don't use it for those types of systems. But you'll see the a's cancel beautifully here. And by properties of properties of exponents, This will become a b to the fifth. So I'm going to say this implies we have 2 over 9, which is 1 over 9 times 27. Yeah, sure, why not? 2 goes into 54 27 times, is equal to b to the fifth power. Now I'm going to help me out a little bit because 9 times 27 is no fun, but I happen to know that 9 is 3 squared. In fact, I'll write that down below. And 27 is 3 cubed. So that denominator is actually 1 over, or sorry, the denominator itself is 3 to the fifth. So it's 1 over 3 to the fifth is b to the fifth. And then to find out what b is, just take the fifth root of both sides. So that 1/3 is equal to b. I now know what the base of this exponential function is. And just like any good system of equations, you can take that b and plug it into any of the equations in the original system. I think I'm just going to plug it in the second equation just because I want to. So I'll erase that out there. Doing that, we get the following. 2/9 is equal to a times b to the third. b is 1/3. And we're going to raise it to the third. Well, that just implies we're dealing with 2/9 times 1/27 a. Multiply both sides by 27, and you will get 2/3 is equal to a. And now I have the full equation, or the function, I guess, for that unshifted exponential function going through those 2 points. The function is f of x is equal to 2/3, that's the a value, times 1/3, that's the b value, raised to the x power. So again, the trick here is you don't have to do it this way again. You could totally have, once you got to this system of equations right here, you could have totally solved one of those equations for a or b. All right, despite that being just 2 examples, that gives enough background for us right now to really gain some ground into exponential functions. I think what I'm going to do is break this review into 2 separate videos. One being for just the graphs, which we just did, and finding equations, which we just did. And the second video will be a calculus-style development of the natural base exponential, which is the base e, which is the most critical base that you can deal with exponential functions in calculus. So let's go ahead and stop this video here to keep it kind of short.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Names for what they are and work together until you feel at peace. Says, listen close, don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.